This video on the Resources of Proof series is a follow-on from the How to Start a Proof video, and in this video we're going to be looking at the syntactic method. In the previous video, I gave a couple of methods as to how to approach a proof, that you're not, when you don't know the idea that you're trying to convey in that proof. Now in this video we're going to be looking at the syntactic method, and we're going to be applying it to a particular example of a theorem. Now, there's also a video on the examples method which uses the exact same theorem, so if you've already watched that video, please feel free to skip ahead to this section just on the syntactic method. There'll be a time code in the description of this video telling you when you need to skip up to. Now the first stage in the how to prove suggestion is the comprehension stage, where you try and understand what the theorem's about and you analyse its logical structure. So let's apply that to this particular theorem. Every convergent sequence of real numbers is bounded. So, first of all, what types of objects is the theorem about? Well, in this case, it's going to be about sequences of real numbers. What are the assumptions? Well, we're assuming that that sequence is convergent, and we're concluding that it's bounded. This has a very simple logical structure, just convergent implies bounded. Let's write out the definitions involved. A sequence of real numbers is, for every natural number, there is a real number, an. Convergent means that there is an a in R, such that for every epsilon greater than 0, there is a natural number big N, such that if little n is greater than or equal to big N, the terms an are only epsilon away from the little a. And bounded means that there are two numbers, L and U, such that every term in the sequence is between those two numbers. They bound the sequence. The next stage, reworking the definitions, isn't that useful in this case. We can look at the definition of bounded, which we could rewrite. Instead of having two bounds, bounding above and below, we can just have one bound bounding the absolute value. This is the same thing as the other definition, but the two definitions, bounded and convergent, don't really seem to play nicely together. One is about the entire sequence, whereas one is only about end terms of the sequence after big N. So how do we get those two to play together nicely? Well, let's use the syntactic method to get that idea. Now in the syntactic method, you work out the structure of the proof using the statement of the theorem, leaving gaps for the objects and arguments that you aren't sure how to do yet. You then fill in those gaps, not necessarily in the order that they appear, and then you turn that process into a full proof. So, the structure of the theorem is convergent implies bounded. So, since it's quite a simple logical structure, let's try a direct proof. We're going to start by assuming that we have a convergent sequence. We're going to be using the definition of convergent to define the bounds, and then we're going to be checking that those two bounds actually do bound the sequence, and that will give us our conclusion. So, here's a proof skeleton. Blank 0 is for the epsilon in the definition of convergent. Blank L and blank 1 and blank 2 are for the L and U in the definition of convergent. And blank 3 is for verifying that that those L and U's are actually bounds for the sequence. So let's fill in those gaps. I'm not sure what particular values we're going to be using in the proof, so let's just try by guessing, say for example, epsilon is 2. And let's use u is equal to a plus 2 and l is equal to a minus 2. So we can then use the definition of convergence to interact with that definition. So if we have an n greater than, little n greater than big N 0, then we have that the terms in the sequences are between L and U. But what about little n before N0? Well, there are only finitely many of them, so we can alter the L and U to cope with that. So let's do that. Let's alter the L and U. Here's our second attempt. We're going to keep epsilon 0 to be the same, 2, and then instead of just picking U to be the limit plus 2 and L to be the limit minus 2, we're going to include the terms before the big N 0 in order to deal with that issue. And then we'll be able to use the definition of convergent after N0, and we'll still be in control before N0. So then gap blank 3 becomes much easier to deal with. So that's the idea behind this proof. Let's turn this into a full formal proof. Now I'm not going to go through this proof in detail. There's an annotated version available in the written resource on this topic. I am just going to say that in this proof I've written it using words and sentences, and every symbol that I've created I've clearly defined in the proof. And this will make it a lot easier for someone to read it. There is another video available on the examples method, as I mentioned before, and a written version which goes into, for example, the writing up stage in more detail. Thank you.